Okay, so we would like to give an expression for the logarithmic derivative of the zeta function that will get us close to the Chebyshev functions. For this reason, it might be a good idea to start by recalling the Chebyshev function. So we have the function theta of x, which is the sum over all prime numbers that do not exceed x of the logarithm of p. And then we have the function psi of x for all prime powers that do not exceed x of logarithm of p. And actually, the truth is that this second function is traditionally given in a slightly different way by the so-called von Mangold function. And the von Mangold function is defined by zero if n is not a prime power, and logarithm of p if n is equal to p to the k for some prime p. And some number k greater than or equal to 1. Okay, so this is the von Mangold function. And we can see that we have this alternative expression for the function psi. Okay, let's go now to the function zeta. And the function zeta, as usual, is defined at least for complex numbers whose real part is greater than 1 by 1 over n to the s. And it's also defined by an Euler product. And all of this is true for real part of s greater than 1. And we would like to know what the logarithmic derivative is. So remember we said before that if a function is a product of functions, then the logarithmic derivative of that function is the sum of the logarithmic derivative. So here we should expect to get the derivative of 1 over 1 minus p to the negative s over the function itself. And what is the derivative? So the usual rules for differentiation tell us that this is going to be 1 over, so there's a minus here, the square of the denominator. And then we have to take the derivative of the denominator. And that derivative will be negative p to the negative s times the logarithm of p times negative 1. And all of that needs to be divided by 1 over 1 minus p to the negative s. So obviously there is a cancellation between this and the square. And we should count to see that we have 3 negative signs here. So it's 1, 2, 3. So all of them multiply out to give us a negative sign. And we have sum of p to the negative s times log p over 1 minus p to the negative s. And here, and this is over all prime numbers. Now we do the following thing. We take this part, and we realize that what we have here is the sum of a geometric series. In particular, 1 over 1 minus x is 1 plus x squared and so on. And if we take x over 1 minus x, then this is x plus x squared plus x cubed and so on. Okay, so this is the formula that we should keep in mind. And this will become minus the sum of over all prime numbers of p to the negative s plus p to the negative 2s plus p to the negative 3s and so on and so forth. So what appears here, and this is the little miracle that shows how useful the von Mancolt function is, that if you think at what we get here is we get all powers of all prime powers for all prime numbers. So in some sense, and let me write it, and it will take a moment to realize that this is indeed true. It's because of the von Mancolt function, we get precisely this. Okay, let's think about it. For which ends will be this expression non-trivial? It's if n is a prime power. And if n is a prime power, let's say if n is p to the k, then what do we get here? So we will get the logarithm of p times p to the k all raised to the negative s, which is precisely p, oops, sorry about this. This is precisely p to the negative ks times logarithm p. So it's precisely one of these terms that we get by multiplying a power of p to the negative s by log p. And that's what justifies this. So in other words, we get our final result. This is a sort of discrete expression. There's also an integral expression that we will look at once we give some necessary definitions. But this already starts bringing together things that are linked to the Chebyshev functions, because, after all, remember that psi of x is the sum So this is one of the explicit hints that we see that there is a connection between the zeta function and the prime number theorem, especially given the fact that the limit as x tends to infinity of psi of x over x being equal to 1 is precisely equivalent to the prime number theorem. So all of a sudden now everything should come in focus, everything is connected, and it's really the study of these connections that not only gives rise to different proofs and different insights of the prime number theorem, but more importantly, it also leads to the Riemann hypothesis that allows us to, if proven, to have a pretty good control of the error term that would show up in the prime number theorem. And that's all. Thanks for watching.